Today we'll talk about some of the remaining topics that again will not be on the exam, but this get brought up during one of the lectures. I want to go into a little bit more detail about what I know, specifically about quantum computing, and then we'll move on to assignment 3, and we'll do some Q&A on that. I'm hoping that you at least get to look at the assignment because as I told you earlier, if you come with question, I'll answer your question. If you don't come in with questions, then you're not going to get answer to your questions. Regardless of these, basically let's move to, I guess, not the last topic of this class because the last topic was from last week. This is like the extra things I want to talk about. Disclaimer, the X interface was gone. So let me double check that I can see your chart quickly. Wait, I cannot see Webex at all. Do you happen to see my screen? I'm not sure if it's sharing or not. Okay. Okay, so you see my screen. All right. Let me move the chat windows over here. Let's see if this works better. Yeah, perfect. All right, so quick disclaimer, I will focus on things that I think I know, which is the hardware side of things. We're not going to talk about the algorithm, which I have no idea about. And definitely, I'm not a physicist, so I'm not going to talk about physics here. These are excerpts from one of the... So this is not a paper. It's more like a... It's actually, I think, was taken as part of the talk. The author is a professor from Caltech, which is one of the top institutions in both physics and computer science. And the paper go into more like an introductory details on quantum computing and what's the way ahead of this field. And the paper is surprisingly pretty easy to understand. It's actually used a lot of like a human language rather than the actual physics and hardware and computer science and algorithm, right? So things that I'm talking about today is actually partially what I learned from some of these materials, including some of the things I've seen in conference talks and some of the topics that my colleagues in the US have done. Right. So first thing is how many of you heard about this thing called Qubit? So qubits basically is what you use to store data in quantum computing. Typically, when you store data, it's stored as 1 or 0, like it's binary. Basically, it means that you have two states. It can be a 0, it can be a 1. Sorry, well, my cat is trying to climb the laptop again. So this is the traditional computer. In quantum computer, the qubit becomes quantum, the bits, the what you store as state. Let me make sure my cat doesn't turn off the wireless. All right. So in quantum bits, you store data through what we call a qubit, where the state is a superposition of state 0 and 1. What does it mean by superposition between 0 and 1? Basically, they follow quantum physics on whether it's going to be 0 or 1. There's a probability of that you're in I'm not sure how should I phrase it, but it's kind of like in the middle between 0 and 1, right? Look at it another way. Basically, one qubit can now store a lot more states compared to one binary bit, 0 or 1, right? And when you perform operations on qubit, this is practically an interesting part because let's say you want to AND, right? You want to AND here. Oops. 0 and 1. What do you get? 0, 1, and 0. You get 0, right? When you AND for qubits, you are essentially doing an AND on two superimposed states. It's not 0, it's not 1, it's something in the middle. It can be 0, it can be 1. And you're doing that AND. It means that you're performing that one operations on multiple different states. So here's the benefit, right? So benefit is basically you can get what we call quantum speedup. It can be used to solve very hard problem because qubit is a lot more stateful. It allows you to pack, if you say so, basically pack more information per qubit, right? So this is as far as I'm aware. NP-hard problems can become polynomial. I think I'm not 100% sure on this. This is basically what scientists are trying to prove, that this is what engineer and computer scientists are trying to get at, right? And to tell the truth, unless you talk to people who actually work on quantum computer algorithm, you're not going to get an answer. The physicists will not really be able to uh, tell you these answers as well, right? So you need to actually develop algorithm specific to quantum computer to get what we call quantum speedup. Essentially, it means that at some point, uh, what we are hoping for is the quantum computer, the performance of quantum computer will be able to catch up. So that's what quantum speedup means. It will be able to catch up to traditional computer, which already with some multiple types of applications, I think the security is already been proved that hey, it's better to run things on quantum computer, right? And another terminology that you might have heard about is called quantum supremacy. Is built in. It's an argument that quantum technology will be able to perform the basically all the computational tasks where no classical computer cannot do, especially the NP-hard problems, right? Where you need to use heuristics, you need to use a lot of guessing to actually make it not NP-hard. Quantum computer might, there's a high chance, high likelihood that they are able to do that. On the paper itself, the article that I sent you, I gave you the link earlier, is actually make an argument saying, hey, it's not proven yet, but it's good to be excited about this possibility, right? So that's where quantum computing is at. What are the problems? Right? It sounds like it's an awesome thing. If you talk to people from the physics world, especially people who are trying to promote quantum computing in Thailand right now, you might get a wrong idea of where the quantum computer technology is, because they seem really, really believing that this is like the next big thing. It is, right? It is the next big thing. But that comes with so much problem as well. And one of the main problems that come with quantum computing is called quantum entanglement, right? And I'll explain what quantum entanglement in a bit. Basically, you have qubits, qubit 1 and qubit 2. Let's say you want to read what's in qubit 1. When you do this, quantum entanglement between these two qubits would dictate that there's a probability that Q2 change its value, right? There's a reading or writing into something, you introduce, why can't I draw this line? Okay. when you read into Q1, the state of Q2 changes. Basically, when you are writing into something or reading into something, the other data flip change. This is a big problem. The reason that this is a big problem is like how can you actually read or write anything in quantum computing without errors, right? This also means that you cannot maintain lots and lots of qubits. The current machine, I think, is up to like tens of qubits, literally like low tens, 10 something. It used to be like 6 qubits, and now it's growing to like tens of qubits. What does this really mean? The next problem is also how to make this general purpose. How can you program, right, on quantum computer? Can you run a normal program on quantum computer, or do you have to rewrite every single piece of code, right? What else does this mean? This also means that you can't really measure the quantum state, basically reading without generating disturbance to other quantum depths. Human readable meaning of this is errors are hard to control. There's going to be so much error. And there's going to be so much error that's where the research is going to head to. You need to be the correct error, otherwise quantum computing doesn't mean anything. It's also going to be really, really hard to scale. Right now, it's limited to tens of qubits. How are you going to have a meaningful computation with tens of qubits? Do you need 50 of qubits, 100 of qubits? So this is possible. Basically, again, disclaimer, I don't actually work in this area personally because I still don't think it's mature enough for computer scientists to like dive deeper in this. I still think it needs to rely on a lot more like physics and actual like science behind how to get this work first before we can build something meaningful. But things can change, and I'm excited about this technology, to be honest. Currently, what we call the state of quantum computer these days, it's called a lot of researchers would call it the NISQ era, which is stand for noisy intermediate scale quantum. What does it mean? It means that your data is noisy, so much error. Intermediate scale means that you're going to have 50 to hundreds of qubits in intermediate size of quantum computing. And what would be the problem with noises? It means that if you look at digital, right, you have digital gates or like you have wires coming in, AND gate, NAND gate, NOT gate, right? Things like this. Quantum computer also have quantum gates. These are the basic compute elements similar to the digital gate or XOR, NAND, and NOR. And please don't ask me how does that work. I actually don't know the physics enough of the physics to actually figure out how does the state between A and B would look like when you have to AND them together. But when you have noises, let's say you have a gate that looks like this. This is qubit 1, this is qubit 2, and you just read to this modified Q2, right? It means that Q3, which is the result of Q1 and Q2, the error will propagate through this gate. So the problem these days in terms of building quantum computers, well, if we accept that there will be noises, how do we limit the impact of these noises, right? Basically, before the errors are everywhere and before it means that the program doesn't run anything meaningful. So the big question is, will quantum supremacy exist, right? This basically means that, hey, at some point in the future, you might not need traditional computer. Quantum computer will kind of like overwrite and be better at running a typical program. And as honest as I can tell, I really have no idea. I think many NP problem will be more efficient over there, but a lot of application will still stick to the traditional computers, how I feel about it, right? And to be honest, if you look at where we are in terms of computing, right? I think the proper solution is this. and this is actually my gut feeling. It might be, I think it's probably one of the correct uh, possibility of what's going to be in the future, which is you run a lot of things in the cloud. Those cloud service provider might start to have quantum computer for you to run things on. And then, depending on the tasks you're running, you will be then steered to the correct hardware that would best suitable running your task. For example, you run machine learning code, they'll obviously be steered to the GPU, right? This is already been done nowadays. So I would imagine that if you want to run something that's NP hard, well, just steer them to quantum computing. The question about how to do that, also how to actually program uh, in a way that your program can be compatible with both traditional and quantum computing, that's a big challenging problem as of now. So that's it for, I think, not today, but actually this semester lectures for computer architecture. We cover so many topics. We're gonna go into the review of all the topics we cover, including what are the topics that be on the midterm, but well, I mean, you know that already, which is basically anything after the midterm will be going into the final. Let me ask you the first question. Do you want final on Monday or Wednesday? Anyone want the final on Monday? Okay, Wednesday, please. Anyone hate the idea of having final on Wednesday? Otherwise, we'll stick to Wednesday. Okay, so any question you have about quantum computer that I can answer, basically you can ask, and if I don't know, I'll say I don't know. And I'll give you time to type while I'm switching over to the PDF so that we can go through some of the homework free material. I need to first stop sharing the screen. All right, do you see my screen with the and be able to read the text? Okay, perfect. Any question about this particular question that I can help guiding you? It's your chance to ask questions that will potentially give you the solution to your exam. I mean, not exam, my bad, to your homework. Like you need to come prepared to some extent, and you need to know what are the questions you want to ask. Otherwise, I'm not gonna give you the answer. Okay, let me ask you another separate question. How many of you actually read through this? Otherwise, I'm gonna give you time to go through this for maybe 20 minutes first before we come back and we'll go through them together if you have questions. Would that be better? Okay. Okay, so how about this? Let's give ourselves maybe 25 minutes for that so that you can read through all the 3 questions and think about the question that pop up in your mind. List them out so that we can go through these questions that pop up in your mind together and hopefully make your life a lot better when you have to actually do the homework. Is that okay? All right, so I am going to be here reading your chat if you have questions in the middle of this, but otherwise we'll resume let's just say 1 o'clock. I think we have enough time to like go through all the 3 questions. When 1 o'clock arrives, basically we'll resume and we'll go through this together. All right. So let me pause this recording so that I don't just record nothing for 30 minutes. So let me resume the recording and find where is my pen. Yep, I need to find one here. All right, so part 8 asks about, okay, how many bits are required to encode the warp ID? In this case, you need to answer in the unit of n, in terms of n. The reason behind that is really the number of iterations in the loop determine how many threads you can do in parallel, right? So if you want to basically say, hey, I'm going to do this entire loop in parallel at once, right? You can. And let's say you have n iteration. You notice that there are 64 assembly lanes, which means that there will be n over 64 warps because one warp is 64 threads. Basically, the number of bits is going to be the log of that, but don't forget to put the ceiling here, because log is, it doesn't have to be a full number. You put a ceiling there to get the number of actual bits. So that's for the first question. For the second question is actually pretty simple. So you look at the second question, what we ask here is basically, okay, this is the pattern, right, that we have. The array A is A of I is just a bunch of 1, 1, 1, 1, 1, 1, followed by 2, 2, 2, 2. There'll be 20 of this, 20 of this, and then 24 of this. 24th of the 0. There are 2 instructions, 1 and 2, right? And one thing you know for sure is this first instruction is the if else, right? Which means that every single walk has to execute the if else. I need to check my condition. So this is always 100% utilization, right? But this is going to be executed if true. And if you know this pattern, it's only true 24 times of it, because when there's 0, that becomes true, otherwise it's false. 1 is not divisible by 5, 1 is not divisible by 4, 2 also is not divisible by 5 and 4. So it's only divisible with 0. So this means that 24 of them will be running instruction 2, and 64 will be executing instruction 1. Out of, in total, you can have 2 instructions that would be running 64 of them. But basically 2 instructions, instruction 1 and 2, that can be fully utilized across the 64 lanes. So this comes down to 88 over 128. And whatever percentage is that becomes the answer to this. So let me go through the third question just in case. Right? Is it possible for the program to use utilization 100? This basically means that A of I is going to be divisible by 4 or 5, right? If this is true, then it will go into the if and run this instruction. It means that yes, as long as a of I are all divisible by 4 or 5, or a of I are all not divisible by 4 and 5. Why is that the case? Basically, it only executes instruction 1 and skip entirely instruction 2. That's also simply utilization of 100%. I know I don't have to run the if, I don't have to run it. Any question about this particular question? Because that's how you work through it. So you can answer part D and E with the same thought process. All right. Any questions? Otherwise, I will start the second question here. This is a little bit harder, I think, I mean, personally, but it's not too bad. Basically, you know that it's a 16-bit address and it's a three-way set associative cache, right? It's a write-back cache. Write-back cache means that we need the dirty bit. What does it mean? Basically, it means that if I modify the cache, at some point, if the cache block is dirty and someone else needs the data, I need to actually propagate the writes down to DRAM. LRU reflection proceed. The true LRU means that if you have the three-way cache, there are in total, basically in total 3 factorial combination of the LRU of all blocks, right? So to work through this question, this is one thing you can do. Basically, you know that, hey, if you look at your address, it's a 16-bit, right, address, which consists of the tag, the byte in block, and the set bit, right? So let's say this is T, this is B, and this is N. You know that T plus N plus B is 16, right? So one thing you know is for sure you need one valid bit, right, per block. You need one dirty bit, as I said earlier, per block. You need ceiling of block 3 factorial, which is 24. This comes down to 3 bits for the LIU. And number of cache set, because we know that there are n bits for this. This is 2 to the n set, right? Each set there are 3 ways, which means that in total there are 2 to the n multiplied by 3 cache blocks, right? there are 2 to the n multiplied by 3 cash blocks. So the size of the tax store, if you look at the question, the size of the tax store happened to be 264 bits. Okay, 264 bits. So what's the equation for the size of my tax store? Well, first of all, you need to know that there are 1 derivative multiplied by 3 multiplied by 2 to the n. That's number of cash blocks, right? Plus 1 valid bit multiplied by 3 multiplied by 2 to the n, right? So that's the valid bit. This is the dirty bit. This is 3 multiplied by 3 multiplied by 2 to the n. This is the LIU bits, right? And then there are T in total, T for the tag bits, right? So I'll just combine, I'll just combine this with the LIU bits because they are kind of part of the same group of data. So you will get T, right, plus 2 of this multiplied by 3 multiplied by 2 to the n. Oops, not T plus 2, T plus 1. So that will be 3, 3, 3, 1, 2, 3. So you multiply everything together, you get 9 plus T, everything multiplied by 2 to the n. 9 plus 3T because 3 goes multiplied here and here, so that's 3T, that's 3. That's also 3 multiplied by 2 to the n, 3 multiplied by 2 to the n. So in total is 9 plus 3T. You can basically start from there. We will get that 9 plus 3T multiplied by 2 to the n equal, what's it, 264, which again happen to be equal to 2 to the 8 plus 2 to the 3. If you solve this out, basically if you solve this out, you actually get that T is 8 and N is 3, then you can get the number of bits for B. Any question? And this last question is actually the same as our cache coherent practice. I just want you to make sure you can do this on your own, because I can assure you similar types of question across all this collection of things that you've seen here will potentially variation this will appear on your exam. So that's basically it for today. I was expecting to actually get proper questions, which I have not. Anything before we basically, anything you would like me to cover that now that we have maybe like about half an hour left? Otherwise, that's it for the material today that I prepare. It's a lot sooner than I expected. right. So if there's no more questions, I'm gonna be basically here looking at potential question from you. Otherwise, feel free to head out. Finish up last set of homeworks, projects, prepare for your midterm. No, not midterm, final. Okay, my brain is going crazy. And then make sure you are aware the exam is on Wednesday. It will be 24 hours. We will go into more details about the exam format. This Wednesday, we will do a review of the topics that we covered so far. Plus, if you look at this homework thing that that I'm trying to go through the answer and you still have questions, let me know so that I can help you through the last homework. All right. Anything else that you want to discuss? Otherwise, that's it for the class. I will again be here until 2 o'clock in case you have questions. All right. Thank you.